Alright, good afternoon students. So I do apologize for not finishing my slides earlier and in class, so I'm trying to provide this quick run through the rest of the slides. So for each of these remaining slides, I do and have provided you with areas that I require you guys to read, so please pay attention to these since we're not able to fully and cover each of these in depth in class. So I've provided the reading that you should be able to do. Now we've ended at the non-competitive antagonist slide that you see here, and recall that the resulting concentration response curves that you would see in the presence of non-competitive antagonists would primarily reduce the efficacy of the agonist, okay, because of that non-competitive nature. They're not competing for that active site, okay? So it's essentially taking that receptor out of the game, okay? And you all know how to find the efficacy on each of these particular lines, okay? And that just indicates increasing concentration of a non-competitive antagonist, okay? Even the pink line down here would be even further, okay? In some situations, okay, especially if there's spare receptors operating, you may also see the potency of the agonist change a little bit as well, and that would usually indicate or be indicated by a reduction, okay? And also with spare receptors, you may also see both the efficacy and the potency being reduced at the same time, but the primary one you should focus on is the one that's highlighted here, the reduction in the efficacy of that agonist, okay? All right, next slide. Let's go. So the allosteric modulation is something we've already talked about, so I'm not going to cover this slide too much, but please keep in mind keep in mind that you still need to cover this. We've already covered it pretty much, and we'll continue on with this particular lecture. Okay, so here is just a summary of some of the resulting lines that you would see either in the presence of a competitive or non-competitive type of situation. Okay, on the right-hand side is when we see two different instances of allosteric modulation. And remember, we can either have antagonism, where we have a reduction, okay, in the efficacy, okay, because we're basically operating in a non-competitive situation with any allosteric inhibitors, okay. But sometimes, and remember, when we talked about benzodiazepines, we talked about allosteric potentiators or activators, okay, meaning that it makes the particular receptor more sensitive to the agonist, okay. It potentiates the effects of that agonist. So in that situation, okay, we would actually see a shift leftward, okay, in the line, okay, because that particular allosteric potentiator or activator assists the agonist in producing a maximal effect, just like we see with benzodiazepines. So if you see a shift in the left, that indicates that there's likely allosteric potentiation or allosteric activators present, okay. Now, for non-receptor interactions, we didn't have a lot of time to discuss this, but I'm not going to cover it too much, but I do want you to know what they are and provide a couple of examples. Now, these are ones that are, they basically inhibit the ability of the agonist to initiate a response, okay? But they don't necessarily bind to the receptor, okay? They can basically interact directly with the agonist itself, or they may basically inhibit some molecules or enzymes that are downstream of that receptor if that receptor was activated, okay? So we could basically oppose the pathway or the action of that agonist, okay, without actually directly modulating that receptor itself. And we can do this through two different mechanisms of non-receptor antagonism, and that includes chemical and physiologic antagonists. But please definitely read that particular slide or that set of pages there. Our chemical antagonists we've talked about briefly in class, but they essentially are molecules that sort of counteract the effect of another through chemical interactions. So if we have an agonist, our chemical antagonist could go in and counteract that particular agonist. An example of this could be heparin. Okay, if we're thinking of heparin as our agonist, we can think of protamine as a molecule that interacts with heparin, which is our agonist, and because of that interaction, we can basically inactivate heparin because heparin is most active and able to function because of its negatively charged molecules. Okay, that negative charge is crucial for its function, and basically protamine can deactivate that by interacting with it and sort of neutralizing or masking that negative charge. Okay. Now, physiologic antagonists are ones that basically exert an antagonistic effect, okay, indirectly. Okay, we're going to talk indirectly here by stimulating an opposing pathway. Okay, that's one way. Okay, the second way here, that's a number 2 that I just drew. It can also do this by blocking a downstream receptor. Okay, a downstream receptor. Remember, many of our receptors produce signal transduction and that signal amplification. Well, if you antagonize any of that downstream pathway, then that's what we're talking about. It's blocking that downstream pathway that particular receptor would have activated. Okay, a good example of this might be glucocorticoids. We know glucocorticoids elevate blood sugar levels, but for instance, insulin reduces blood sugar levels. That's an example of this first one here. Okay, it's antagonizing the effect of another. Okay. Now, in some instances, this is one thing I want you guys to star this, and definitely go and read these pages here, because I want you to see what is written in these particular slides. We'll cover it in the next one, but remember, we've talked about full agonists and we've talked about partial agonists, okay? But let's think about what happens if you have full agonists present and then all of a sudden you start adding some partial agonists, okay? What happens, okay? Well, if you have a partial agonist that is present, okay, after there is already a full agonist there in the system, what you're going to see is that that partial agonist behaves very similar to a competitive antagonist. Okay, well, why is that? Think about it. You have a full agonist that's there producing a maximal effect, but now all of a sudden a partial antagonist is introduced into the system and is competing for the active site. Some of those molecules will successfully interact, but because they only elicit half maximal response, you can have a reduction in the response for that particular concentration. So essentially, a partial agonist can sometimes look like an antagonist, okay, even though it's not truly an antagonist. Okay. Another key point that I want you to underline is that partial agonists may or may not have greater potency than a full agonist. Okay, so don't always assume that a partial agonist is going to have a lesser potency, because sometimes it actually has a greater potency than a full agonist. And a good example of this is morphine and buprenorphine. Okay, so what I want you to take a look at here, I've already left some lines up and everything. Here we go. But essentially, in this situation, buprenorphine is our partial agonist. Okay, our partial agonist. Why is it our partial agonist? Because it does not, or is not able to achieve the maximal effect that the other drug is, okay, which is morphine. Morphine's maximal effect is right up here at 100. Okay, buprenorphine is just about half of that, so therefore buprenorphine is our partial agonist. But if we say, okay, here's the maximal effect of buprenorphine, and it's 50, okay, to find its ED50 effective dose, remember effective dose is how we find its potency, okay, that would be 25, because that 25 is half of 50, okay, and where those lines intersect, there you go, right in that little spot, and we draw our line down here, and there's your ED50 for buprenorphine. Okay, now what about for morphine? Okay, morphine, to find the effective dose 50, we would take half of its effect, which is 100. So let's find where it crosses 50, because 50 is half of 100. Oh, and the line is right up here. Okay, right there in the little circle I just drew. And you draw our line down, and there's our effective dose 50 for morphine. Okay, the effective dose 50 for buprenorphine is less than that of the effective dose 50 for morphine. Therefore, buprenorphine has a higher potency, okay, because its ED50 value is smaller. Okay, so we can see in this situation that buprenorphine can have a higher potency even though its efficacy is nearly half of that of morphine. And when we get to CNS, we'll talk about the reasons we like to use buprenorphine as a nice medication to help assist in individuals struggling with opioid addiction. Okay, and we'll talk about why, but I just want you to understand from this example that partial agonists may not always have greater potency than a full agonist. Okay, sometimes it does, sometimes it doesn't. Okay, so that's the key thing to take away from here. Definitely read these pages down here at the bottom. Okay, so partial agonist hypotheses. Okay, now why is it that partial agonists may stabilize receptors in an active state but still not able to produce a full maximal effect? Well, it turns out there's several hypotheses. For instance, one of these hypotheses indicates that some of these receptors may still be in an inactive state even though a partial agonist may have been bound or interacting with that. Okay, so in some cases, one of the hypotheses indicates that these partial agonists may be bound, but some of those receptors that have a partial agonist bound may still, be in the inactive state. Okay, another theory is that while some of these partial agonists may stabilize the receptor into an active state, there is the hypothesis that there can be multiple conformations that are considered active, and some of those may not be the maximal active conformation, while some could be submaximal active conformation. Okay, think of it like pressing down the gas pedal of your car. Some of those partial agonists may be able to depress the gas pedal only about halfway. Okay, you're still activating the acceleration of your car, but again, a full agonist would be one that would basically push that gas pedal all the way down and you would have full activity. Okay, so some of these partial agonists may not be able to stabilize the receptor in its most active conformation. Okay, so there can be multiple conformations. We've talked about this, but that's kind of some of the hypotheses that are put forth on why some of our partial agonists may not be able to establish or elicit a maximal response like our full agonists do. Okay, we've talked about spare receptors. I'm not going to necessarily go into this slide too much because we've already talked about it. There you go. Definitely read pages 24 and 25. Pay close attention to the fact that spare receptors allow for full efficacy for a particular receptor system, and it does this because we've talked about signal amplification. Only a few receptors can be active to basically amplify that signal, and because of the way cells operate, is that amplification can be so pronounced that it can definitely get to a full response without the need for all of the receptors to be activated. Okay. Now, a good way to see this on these particular concentration response curves is if you look at these particular concentration response curves, and remember we compared KD, right? We know all about KD. That's the concentration at which half of the receptors are occupied. We talked about EC50. That is the concentration necessary to produce a half maximal response. So if we think about it, if KD pretty much equals EC50, then that basically means that there's a linear relationship to the occupancy to the efficacy. Okay, and that would indicate that there's probably almost a one-to-one or linear related effect to receptor occupancy, and that might indicate that there's very little spare receptors taking place. Okay, however, and definitely star this, if our KD value, okay, remember that's a concentration, is much greater than our EC50, okay, we can see this right here, okay, our KD value is much greater than our EC50 value in this chart at the bottom, then what that would indicate is that the effect that we see, okay, the concentration necessary to produce a half maximal response is much smaller than it is needed to basically occupy half of the receptors. Okay, do you see that difference there? Okay, KD value is higher than EC50. Okay, if you see that, okay, then that's a good indication that you do not have to occupy all of your receptors to produce half maximal response. Okay, and you can translate that up to the maximum response. Okay, and this would mean that this is a non-linear relationship, which would be a good indication that yes, spare receptors are probably present, okay, or at play. Okay, so this all kind of boils down to the fact that the maximal response or our efficacy is something that can be achieved with a drug concentration that is less than needed for receptor occupancy at 100%. Okay, so that is one easy way to determine. Okay, so definitely highlight this. I'm just going to put that in there. Okay, you'll probably receive a question on the exam or a quiz, something like that. If KD is greater than EC50, okay, you can expect that it's very likely spare receptors are at play. Okay, I've already given you some examples of spare receptors. Read this one, also read those pages down at the bottom. And so when we take a look at this, when we start adding a non-competitive antagonist to a system that has spare receptors, okay, initially when you start adding a kind of a low concentration of non-competitive antagonist, you might see a shift in the right. Okay, we can still achieve maximal effect because we still have some spare receptors. Okay, we haven't blocked those spare receptors yet. Okay, if we add a little bit more of our non-competitive antagonists, we may see a further shift in the right. Okay, but if and when you receive or administer a concentration in which you are inhibiting all of the spare receptors present, then at that point you're going to start to see a reduction in the efficacy. Okay, once you start inhibiting all of the spare receptors, okay, then concentrations of non-competitive antagonists after that, or greater than that, you'll just start to see a reduction in efficacy, and that's indicated by a reduction in the efficacy, or that plateau that we see. Okay, this is some of these examples that you'll see on your practice problems. Okay. Now, for this right here, this is a practice problem that I want you to attempt. I've just given you, okay, the answer for dopamine here, okay, but you're going to have to use this puzzle to figure out what haloperidol is and what aripiprazole is. Okay, so this little pink line that I've got starred right here, for right now I want you to ignore that, and we're only going to focus on the red line, okay, red line right here, and of course the green line right here. Okay, so the key thing is we see when we start off on some of these lines, we're starting at 100%. Okay, that's the red line and the green line. Okay, the reason is because dopamine is our full agonist. We're already starting off at a concentration that is basically putting those receptors at full efficacy. Okay, but now we're starting to add more and more concentration of whatever compound is listed in the brackets. Okay, so for instance, this line right here, this blue line, okay, if we don't add dopamine, but we're starting off with aripiprazole, okay, we see our blue line kind of sitting right here somewhere around 20%. Okay, and then it eventually starts to increase, okay, but it only goes to about right there. Okay, the green line, we also have dopamine, that's why it starts off here at the top and begins to decline. Okay, but we're adding more and more haloperidol. Okay, so as you can see, once we start adding more and more haloperidol, we see a reduction. But it's your job to tell me what these drugs are. Okay, and you have to tell me whether they're a full, partial, inverse agonist or an antagonist. Okay, and please explain your answer. I will cover this. I will probably before Wednesday or even this afternoon at the review period, I may post the response or the answers to this, but I do want you to try to classify these yourselves. This is a good example. You may see something like this on the quiz or the exam. Okay, so that's all I have for you. I hope I kept this to 10 minutes. I probably did not. I don't see a time right now, but please forgive me if it's not 10 minutes, and we will see you in class. Thank you.